Hello guys, thanks for coming back for another exciting video. I'm just kidding about that excitement part, but this is some complicated stuff to think about. If this is the first time, one of the first times you've thought or heard of quantum numbers and how they describe the locations of these electrons traveling around the atoms or existing stably around the atoms, you may have to practice a lot. It takes a lot of practice and honestly a little bit of memorization. Um, All right, rewind the clock. Classical physics, classical science, where we think we know and we know we can know if we have enough information exactly where something is and what it's doing at any particular time. So as the batter hits the baseball and travels a parabolic trajectory, we know quite well how to describe that travel. We know the particle, the ball, will be in exactly one place at one time. But you know what? It doesn't always work that way. That's in the olden days. This is the new idea of the quanta, or the statistical probability that an object will be in one place at one time, doing a particular movement or situation of energy. And it applies especially to small particles. And when the particles get small, like electrons and atoms and such, um, we talk about the likeliness of it being in one place as opposed to another. And that introduces fuzziness, blurriness, unknowability, unpredictability, a statistical chance that the ball or the object will be in a location. So here we're using a classical macroscopic thing like a baseball to say if the baseball were behaving in a quantum mechanical manner, there's a 70% chance it'll be in this ring and a 40% chance it'll be in this ring. And so we're talking about statistics and likeliness. I don't mean to confuse you. The ball is not statistically variable like this, but if it were the size of an electron and the electron were existing in this region, then all we can do is talk about statistics and probability. And speaking of electrons, these things called wave functions. We think of an electron as a particle, but in actuality it's so small and it has a totally different character to it as well as a particle. It has a wave nature, a wave character. And that wave character, it turns out, is super important in helping describe why the electron can exist around the proton. This phi function describes the locations where those electrons can be in a stable atom. E is the total amount of energy in that electron, and H is this funky operator that helps satisfy the sum total of the kinetic and potential energies. When we take this function and square it, we actually get a quantity, a handle on the probability that it'll be a certain place, and it describes what we call the orbitals. To solve this wave function, this wavy thingy describing where the electrons are existing, we could say traveling, but I'm not quite so sure they're traveling like a particle. It turns out in the mathematics is a little bit beyond this course, so you have to trust me on this one. There are three integer quanta numbers that come up, the n, the l, the s. One of them describes the size of the orbital, the size of the location where the electrons chill in. The other one describes the shape of that orbital, and in some cases the m sub l describes its orientation in space, although the simplest orbital doesn't have an m sub l, or I could just say its m sub l is 0. Oh yeah, the principal quantum number just describes the shell. The first shell is closest to the nucleus, the second shell is outside of that, the third shell is outside of that. And in this equation from our previous video, we described the energy level of quantum main shell n as this constant in joules times 1 over, and that's the number of protons for hydrogen is 1 over the energy level squared. So that if I'm really looking at hydrogen, I look at energy level 1 as that constant times 1 divided by 1 squared, or that constant RE times the second energy level squared, and on up, and they get less negative in energy. And if this electron were to go a little bit further away, we could say it would be ionized, and the energy sort of goes to 0 out there, the potential energy. The angular momentum quantum number is a little funky as well. It describes, well, as as its name implies, some kind of value of angular momentum, and these come in integer numbers. So, like n could be 1, or 2, or 3, or 4, or 5, or 6. So too can L, but L can actually have a zero term. And again, all this comes from mathematics, so you'll just have to trust me on it and try to struggle through some examples. Um, if the L value, L quantum number is 0, we call that a shape, an S-shape orbital. If the L is a 1 in larger quantum n numbers, then my L equals 1 is described as the P-shaped orbital. L equals 2 is a D-shaped orbital. 3, F, 4, G, 5, H, 6, but no atom is large enough to even need a G orbital in its ground state, and so any orbitals beyond L equals 4 or even L equals 3 are excited atoms. There's also this magnetic quantum number that describes the orientation in space along the x-axis, along the z-axis, along the y-axis, somewhere in between, and that can vary from as small as negative L through 0 up to positive L. We'll see a bunch of examples of that eventually. In describing these locations where the electrons can go, we sometimes call them orbitals. We sometimes say the L values are the subshells, and N, the principal quantum number, is the main energy level. Here's another diagram, but this might not, I don't know if I like this one or not. You can look at it and see what it's worth. The first level is small, and in a sense it only has, closest to the nucleus, only has an S orbital. The second level, n equals 2, has two s orbitals, which are right outside the 1s orbitals, but it also has two p orbitals nested upon that and kind of mingled and mixed in terms of overlap. And layer 3, the n equals 3, has also L equals 0, that's the s orbitals, just like the 2s and the 1s, but it's a little bit larger, nested outside of that. And yeah, also some p orbitals, just like layer 2, and also layer 3 had d orbitals, so 0, 1, and 2, because L can be up to 1 minus n. 1 minus 3 is 2, and there's the 2. 2 minus 1 is 1, there's the 1. Interesting. These M sub L's 0, 0, 0, or negative 1, 0, positive 1, negative 1, 0, positive 1, or in the case of L equals 2, M sub L could be negative 2, negative 1, 0, positive 1, positive 2. We need a picture of what all this means here, really quick like. So in the motions of the electrons, I shouldn't say motions, the existence of the electrons in specific orbitals around the nucleus, sometimes they could be bumped up or jumped down. They like to stay as low as possible to maintain the lowest possible energy, but if a photon of delta E equals E1 minus E3, if the photon of just that energy comes up, it could bump up that electron to a higher level, but the electron wouldn't stay there for more than a moment. It would come right back down. It might fall all the way back down to level 1, or it might just jump down to level 2 temporarily, giving off a photon of this energy. And these transitions are even given names. The specific, I forget the names, honestly. They're on a different video, or did I have them here? I don't know. The bigger the energy jump, the bigger the energy. So ultraviolets have a lot of energy. Smaller energy, smaller energy. Oh yeah, this is the ionization energy, to take the electron from level 1 for hydrogen all the way to infinity, or far enough away from the nucleus it doesn't feel its effect anymore. Let me pause just for a second, ladies and gents. Hey, here's an example of such a calculation. Calculate the wavelength of light emitted when an electron, well, I could say the wavelength of a photon, or the wavelength associated with a photon that is released. And I say released because if I'm going from 6 to 5, that's higher energy to lower energy, and the electron has lower energy at n equals 5, so it will be an emission of a photon. So in other words, this has more energy than this, or in other words, my delta E was from level 5 to level 6. I can write it out like this. Um, and it comes out to 2.66 times 10 negative 20 joules for such a transition. Then if they really want to know the wavelength, I have to take the energy equals Planck's constant speed of light divided by wavelength and rearrange that a little bit. So Planck's constant is a constant, and so is the speed of light. And the energy I calculated, the negative here just means it's being emitted. Energy is being emitted, so I just kind of dropped it here because a negative number of meters doesn't have much of a meaning. Or another way to work it is I could say, this is for a different transition from 2 to 1, also an emission. Why didn't I do an absorption? I could have. Or if I just switch this from E2 minus E1, that's an absorption. That should come out positive. But the difference is still 1.63 or 1.64 times 10 negative 18 joules. Stick that in the denominator and you find a wavelength like this. How does that compare to the first one? Let's see. This was to the negative 20 joules. So that's lower energy. This is higher energy. Higher energy should be a lower wavelength, so this should be smaller. Yeah, it's a little bit smaller than this one. Interesting. Kidding. I don't know. Probability density. So we talk about the likeliness of an electron. If I took a snapshot, where is the electron likely to exist in the hydrogen atom in the 1s orbital? I'm not so sure. But is there a 90% chance it's in this vicinity somewhere? Let's get into the shapes of these orbitals a little bit. I just want to show some pictures. The s orbitals are all round, spherical, like this. The m sub l for this L equals 0 has to be 0 as well. There's no description of its orientation in space. But if this is the 1s, then the 2s exists outside of that, also spherical. And the 3s exists outside of that, also spherical. And the 4s exists outside of that, even. So it's like eggshells nested upon, spherical eggshells nested one upon each other. And the 1s is closest to the nucleus. The p orbitals look a little different. They look like dumbbells. So this is one p orbital oriented along the x-axis. Here's another p orbital oriented over the y-axis, another p orbital over the z-axis, and I could have some m sub l values here, 1, negative 1, 0, although that's not really set in stone which is which, but usually, we talk about it this way. And you'll also, this one and this one and this one are all snugged up on each other, so this is right here, which is also right here, and those 3p orbitals are also just a little bit higher in energy than this would have to be, was this 3p? They didn't say 2p or 3p. There'd be some s orbitals spherically centered right around that origin as well. So we got the spherical ones, and then we got this one and this one and this one also nesting on top. And the d orbitals get even weirder. It's not just single dumbbell, but a double dumbbell. So I've got, this is one orbital, one orbital, one orbital, one orbital, one orbital. And with L equals 2, m sub L could be plus 2 or minus 2, plus 1 or minus 1, or even 0. Here's a weird, I should have mentioned this somewhere. I think I did that. I'm not going to say it right now. Let me go on to the f orbitals. Stay focused here for a second. And the f orbitals look even funkier than that. So so if this is L, m sub L could be negative 3, negative 2, negative 1, 0, positive 1, positive 2, or positive 3. Oh yeah, I listed it right down here. This one's super cool. I love this one. Call me a nerd. Just behind my back, alright? I don't know what the definition on this is going to be like for you. That's not too bad. But here's a good one to study, to think about. The shapes of the orbitals, the quantum numbers. So 1s is very small, 2s is larger, 3s is larger, 4s is larger, 5s, 6s, 7s is larger. The p orbitals first come into existence on the level 2, and they look like this, or sort of like this, or sort of like this, or sort of like this. Notice they get a little bit more complicated looking. The detailed structure gets more complicated even within the p orbitals, but don't worry about that. Just think about this. And the d orbitals and the f orbitals. Oh my goodness. Guys, I'm out of time. This is taking much longer than I thought. I'm going to have to add a second installment, an exciting supplement to this one. Hey, I'll see you in class. Thanks for watching and studying.